Jon Friskics, and this is the talk that I've made on practical Swift generics. So real quick before I get started into the talk, I work at this company called Code School. Anybody here heard of Code School? Or use Code School maybe? Yes, thank you. So what we do at Code School is we make these really cool interactive videos, interactive challenges to help you learn how to code. We do have a little bit of iOS stuff, but I haven't worked on a ton of that recently. That's part of what I work on here though. But we do have like a whole bunch of other topics that are things that might be useful to you if you are working on something that ties into iOS. Like you've got a lot of questions on Ruby, .NET, Python, things like that. So definitely check out Code School. We've also got an iOS app that's pretty cool. It's kind of a recent development for us for playing all the videos and everything offline. And something really cool happened with that this year. Like we got into a giant wall of apps during one of the WWDC keynotes, which was cool. That was us, like tiny little icon and everything. But it's pretty fun. I like to show everybody that I can that because unexpected that fun. So let's talk about generics. What are generics in Swift or in programming in general? Right, the idea of generics is that it's a way to write classes and functions without having to declare a specific type, but to still maintain that sort of strong type safety whenever a function is called. And really, at the end of the day, what they lead to is they lead to being able to write less code while still having that strong type safety that Swift is known for. That's one of the reasons why you might choose to write something in Swift, right? To have that strong type system and have that type safety. So let's talk first. Like, have we ever had anything like this? A lot of us in here aren't just starting developers that are brand new. Have you ever had anything that are like generics in something like Objective-C? Well, let's take the case of an NS string first. Right, so you have an NS string, you create an object, it's of type NS string. And then later you want to work with that object, and guess what? It's still just an NS string, no matter what you do, right? No matter what you do, an NS string is always an NS string. If you want something else, you declare a new type. But then you have this weird type called ID when you're working in Objective-C. And ID was whatever type you declared it as kind of in the moment. It really could be any type depending on when you used it, what the context was that you used it in, right? So ID was kind of strange like that. And Swift sort of has the same kind of thing in the form of any object or any sort of value type inclusion version of any object. So you declare something as just being any object, any type at all, string, NS string, data, anything. And at any point though, you can change the value of something that's in any object to some new object. It doesn't remember what object type you set it to. Literally can just be anything. So that's kind of where generics live. Generics fit somewhere right in the middle of that, in between a strong type and something like ID or any object. They're not quite right on any one of those categories. So I want to start by just doing a bare bones simple example. And I'm going deeper than this because a lot of the generics introductions you read use this example for one, and it's kind of a trivial, non-practical example of using generics. But it's really cool because you can kind of get a feel for the syntax and how this all works with a simple example. Then we'll dive into some more practical examples after we get the basics down, right? So this idea here is that you have to need to swap two values. So maybe you write a function called swap two ints. In the body of that function, you just go through and assign some things. And really what you end up doing is two ints come into this function, and two ints go back out. And they're just swapped, right? Really trivial function, and probably even way more complex than it needs to be. But it's going to illustrate this point here in a second. So then when you call this, you pass it these two ints. I'll just pass it the numbers 5 and 7. Then if you print that out, what do you get? 7 and 5, right? Just swaps the two of them. Cool. So they say, oh, that's really cool. I can swap integers. I have an app that's going to do that now, right now. Very trivial example. So then you say, oh wait, I also want to swap strings. I don't just want to swap two integers. That's really cool, but I want to do something a little bit more here. So maybe you write another function called swap two strings. Right? It takes in two strings, and outputs two strings. And then when you call a function with your two strings, what's going to print out? The flip version of those two. So you're going along, everything's good, everything's working great, and you kind of have your swap two strings function, and you have your swap two ints function, and then you have your swap two whatever's functions, right? And maybe depending on the amount of things you decide to swap in your hypothetical app, you can have dozens of these functions that are really all kind of doing the same thing, right? They're just taking two things, swapping the position of them, and then returning them. So what if there was a way to generalize that? What if there was a way to write a function like this, where we could swap two things? And we could take thing 1 in and thing 2 in, and return 2 more things just with their position swap. So it's cool, we can do that. We know how to write functions, easy. So we write our function, and it kind of works. The body of the function is the same as those other ones, right? Except we're operating on these objects of type thing now, or values of type thing. What's going to happen when we run this code? We're going to get a big error here, right? It's like, wait, thing isn't real. It's just some word I made up. Could have put anything. There's not a type in Swift that's built in the standard library called thing. It doesn't exist. So what can we do? Well, we do something pretty cool. Like, because we want to declare this type, we could always make like a struct or a class or something that's called thing, give it some properties, methods, and all that. But we don't actually want to do anything. We don't want thing to actually be a concrete type. We want to sort of just be this abstract idea that exists inside the body of the function. So that's where generics come in. And at the simplest form, this is how you do this. So right after the function name in your code, you would write these 2 brackets, angle brackets, right? And you put the name of the type inside of it. And it's called a type parameter. You can do this with any function. And when you do this now, this type thing exists only during the body of the run of that function. So thing doesn't exist like anywhere outside of the program. You couldn't call another function with passing something of type thing. It's like, I don't know what thing is. I've never heard of that. But inside the body of this function right here, thing is an acceptable type, and the compiler is not going to get mad at it. And it's going to accept that. Okay, so what then? So let's see, if we call a function here, something cool is going to happen. What'll happen is that type thing gets temporarily replaced just for the run of that function with whatever type you pass in as an argument when you're calling the function. So here I call a function, the swap 2 things function, and I've given it 2 ints. So during the run of this function, thing is an int. And then I swap those 2 integers for me. Cool. So now I go back, right, and then thing becomes an int for both of these. Int. So then I go in and I write another function, or a quality function second time rather, using the same function signature. And I pass in 2 strings this time, right? And then it reverses them like we'd expect. And thing, that first thing is a string, and the second one, of course, is also a string. So you can see I can use the same function with different data inputs and get the same expected output just on different data types. And I've got type safety that's preserved as a part of that. To give you an example of what it would be like if I tried to do something like this, right? Like here I passed 3 as the first parameter, and hello, a string as the second parameter. So those are 2 totally different types, right? What's going to happen when I do that? It's going to say, okay, cool, thing is now an int. Got it. This is 3's an int. I'm cool. But then it's going to go, oh, wait a minute. Like, I thought you said thing was an int. This doesn't look like an int. I'm very confused, and then you made a nice big error. Hey, I was expecting an int, but you gave me a string. The compiler will just tell you that not let you run your code so you don't have a crash when the function actually executes. So yeah, that's a pretty key thing with generics. Once the type parameter is set, it can't change for the rest of the run of that function. You could of course just call a function again and give it the same types, and that's all cool. So why not use any object then? Any object's always been available. Why go to the extra trouble of dealing with these type parameters and things like that? Well, ID in any object again can change at any time, but once that generic type is set and defined, it's set for the entire running of that block. It gives you more control over your types and how data gets passed around. So in that in a nutshell is generics. That's like one of the simplest examples I can show you for the setup of how you use these things in your code. A lot of it boils down to like putting a made-up type, just that you make up, whatever you want to call it, right, inside those angle brackets. In fact, one of the conventions for it, if you've ever seen code like this, is to use the letters T, U, and V. So like the first just generic type parameter is T, the next one is U, the next one is V, and then you just put the inside of your function block with all the T's, U's, and V's. I try to avoid those in certain places here just to make it a little more readable, but I do have some of them in some of the example code I'm going to show. Cool, so got the basics down. sort of super simple implementation. But if you're like me, when I first got to this point where I understood that part, I said, oh, this is really cool. I can define these like abstract types and put, have one function that performs multiple different tasks with different kinds of data. I was kind of like, okay, cool. Oh, wait, now what? What do I do with this? I'm not swapping integers. Where can I make use of this kind of thing? So the first thing you want to do is you want to look for places where you're writing the same code for multiple different types. If you have an app that you're working on right now, you probably want to open it up and see if you have that duplication in there somewhere. Not just that you're writing the same function for different things, but that it's operating on different types with the same function implementation. That's kind of the key thing to look for when you get started. So let's jump to something else. Let's jump to something else like a stack. This is a generic data structure called stack. So here's how stacks work if you're not familiar with the idea. It's kind of like an array, it just has a few more constraints. The idea is you've got this box called stack. It's going to hold a bunch of different values, right? So you might do something like add John to the stack. And now John is sitting inside of that data structure. Still just kind of like an array right now, right? And then maybe I add another thing, I add Amy to the stack. And that string, here's in there too. There's two things in the stack right now. Then I add another name, I add Greg to the stack. Greg shows up in there. And then, though, this thing is different from an array, I can remove an item from the stack. And you can't arbitrarily pull things out of the stack usually. You just pop the thing off that's on the top. And now it's not part of that data structure anymore. And then if I push another thing onto the stack, then that thing just appears as the next item in there. So there's all sorts of uses for this kind of data structure. UI navigation controller works like this under the hood, right? Like you just keep pushing view controllers and you pop back to go backwards and hit that back button. It's just popping one of those view controllers off the stack. But there's all sorts of places where you can make use of something like this. So here's the code for like a really simplified generic stack. This is using generics. It looks something like this. I just picked struct that be a class 2, and it's got a type parameter t. So t exists just inside of the struct and nowhere else. And then I've got an array of type t objects. So this var stack brackets t here is just creating an empty array, but it's saying inside of the body of this function, the only items that can go on that stack are items that are of type t. And t gets set depending on when you create the stack. So this will work for any kind of object that you can think of. And then I've just got two functions here. One of them is just to add stuff to the stack. One of them is to remove stuff from the stack. And just for this example, so I had an extra piece of data, I also just kind of had an internal count variable, so you could always see how many things were on there without just accessing the array. So yeah, array holds generic type t, push an item t onto the stack, remove an item of type t from the stack and return it. And you get it back as an option usually. So to use it is pretty simple, right? You just maybe have some objects. Like here I've got two view controllers, VC1 and VC2. And I've created a stack. When I do that, I'm actually giving it a type parameter when I call the initializer. So I'm creating a stack and I'm saying, what goes inside those square brackets? That's when I'm calling it, right? Not declaring it. I'm saying T is now going to be a UI view controller all over the place in the stack. Always, no matter what. For this stack variable S. And then I just add my items to it, and if I call the count on it, cool, I've got a count of 2. I've got 2 things that are on that stack. There's my stack down there. If I were to try to pop something off, like I moved it from the stack, now it's gone, the stack only has 1 in it, and then I contains that second view controller that I popped off the stack. UI view controller object. So I can do even more than this though, because that's kind of cool, right? I have this generic thing where I can push stuff on and off. But let's say I wanted to get a little trickier with it. I wanted to say I only want certain types to be allowed onto the stack. Like T suggests that any type that I can ever think of, whether it's a value type, an object type, anything, they can all go on the stack. But maybe I have a certain set of requirements in my app logic where I only want certain objects that have certain capabilities to be on the special stack. So what I can do is I can add a constraint to the type parameter, like you can see on this bottom example here. So now instead of just a struct of t's, it's a struct of t's that conform to a protocol called stackable. And that's like, again, a protocol I made up. There's not a stackable protocol in the standard library. We have to make that protocol, and then we'll be able to use it. So type constraints are really there to just help you restrict those generic types a little bit. And in a way, it's kind of funny, like we're talking about generics and how everything's just supposed to be generic and applicable everywhere. And by adding a constraint like that, we're really making them more specific, right? At least they didn't make a new thing called specifics. Again, we're talking about generics and specifics. That's good. So let's see how we can use this protocol, like how we may be able to implement some really basic protocol and see this working, see this constraint in action. So here's just a really simple example of how we might do that. I kind of try to keep it very simple, not have tons and tons of lines of code on the screen at once. So first we define the protocol. So I create a protocol and I call it stackable, and I just put one variable in it called am I on the stack. So maybe I would set this on my view controller. So when they were added to the stack or whatever. Then I would take my subclass, whatever my concrete type was, and I would make it adopt that stackable protocol. So view controller here is a UI view controller that follows the stackable protocol. And because I'm adopting a protocol, I don't have any optional methods or properties in it, that I have to actually implement those. So here's the implementation of that. I just have an internal variable, and I return if it's on the stack and set it to a new value if I put it in. So this view controller conforms to that protocol now, which means that our stack should work is with that type constraint, as long as whatever object we try to put on top of it conforms to that protocol. So let's see what happens when we do that. There's our class protocol instruct again. So here I created an S1 stack, and I said that it's a stack that's constrained to be just view controllers that are of type stackable, adopt the stackable protocol. And it looks at it and says, okay, cool, yeah, view controller is stackable. Cool, I'm going to allow that to happen. That's what the struct is saying to itself right now. So then what if I added something like this, and I said, oh no, I want a stack of UI buttons now. It's going to be able to upset about that. It's going to say, hey, this is the exact error you would get, right? So, hey, UI button does not conform to protocol stack. So here I've made a generic stack that's constrained to just objects that follow a certain protocol, therefore giving me that much more control. And that's kind of a preview of what you can even do with constraints. You can go even further than that. You can have where clauses inside of that, and even further narrow down all the requirements for something that, for an object that can be used in the place of a generic type parameter when you call a function, or when you call create an object or create a data set. So network responses are another place that you can make use of generics in some interesting ways. So I want to show you an example of that. I'm going to walk through all the pieces of this. Anytime you start dealing with a network request, right, it starts to be a lot of moving parts. So rather than have all the code appear, in pieces, I've just sort of started that network request. And we're going to kind of walk through the pieces and see how we might be able to use generics to deal with the response in a more intelligent way, in a more type-safe way. So here's where we start. We just got a function that takes in a URL string. So this might be a function that you call and you pass, google.com into. That's where you're making the request for data. So first inside of there, pretty standard stuff. This whole part right here is not any generics yet. We're going to kind of refactor this to use that. But you might check if the URL string actually is real and exists, and then you maybe make your request, and then you've got a closure that returns the data response and any errors that would happen. Pretty standard URL session request. And then you would use that request, or use the response rather, that you get back from that data test, right? And maybe you first check there's an error, and if there is, you print it out. And then you make sure that your data actually came back, and sometimes what will happen, right, is that there won't be an error, but your data isn't what you expect it to be. You don't actually have data that came back. So you want to check that first before you try to use the data. And then you take your data, and I'm just doing something simple with it. You're turning it into a string, so I can just log out of the console. And then calling that function is really simple, right? Just call make request, pass the string, and it's gonna, if it gets data back anyway, it's gonna pull that down. And the example I'm using here is that you have sample code for this that I'll post online with a PDF of the presentation. This is a cool service, http://stat.us, and you just put / some HTTP code after it, and it will return you a response that has those correct headers in it. It's like if you want to simulate a 404, you don't have to actually remove a file or put a bad URL it'll just return that mock response for you. Really, pretty cool for coming up with demos and stuff, especially. Okay, cool. So what's wrong with that? It's pretty standard implementation of a simple network request. What are some things that we can do better with that? Well, for one, we don't really have much control over our response data. Like our response just comes back as something, and we just have to trust that we can turn it into a string even, or turn it into some correct type of data that we want to be able to do something with it. This case, it was just printing, but in a lot of cases it won't be printing, right? It'll be taking that data, just mangling it into some other format, maybe updating it to a table view with it, something like that, right? Also, what's going on in there, it's a little messy, is that the logic of the processes of the response is also like in the request code. So you have all this stuff in one place, and you have this really big function that you start building out with all the logic you'll likely need. It's going to be really messy. It'll work fine, but it'll just be messy. So let's tackle maybe that part first. Let's get the messiness out of it first, and then do something with generics to make the response even easier to handle. So the way we usually do this is something like completion handlers, right? In our function, instead of just passing a string, we might write a completion handler that takes in a string and then returns some stuff, or doesn't return anything. It just does something with the response without returning it. And then inside of there, instead of just logging out the message, we would call a completion handler. And here, I'm just passing the message bad URL. That would be the situation right there, right? If this scarlet URL isn't true, it's not able to expand URL out of that string that came in, then that would mean that I just maybe typed in a bunch of random characters that nothing like the URL would have been useless to work. So then we keep going and we pull down and we do kind of the same thing whenever we have our error inside of the response block, right? We would call the completion handler when we saw that error in there. Here I'm just passing that string with the error. And then when I have that success response, I do the same thing. So it's really that same code as before. I'm just passing in this completion block that I can call at the time that I call a function, not inside of that request block. So I just call this completion handler, passing in response, and the response will just come through. And I can print it out to the screen. Cool, so I kind of decouple those two things, and that satisfies that problem of having the request and the response in the same place. But in this example, I'm still just kind of being messy with it because I'm still just using strings. Error was a string outside of the request, error was a string inside of the request, error was a success was even a string. So if I wanted to inspect whether I got a success or an error and do something with that in the response handler, it's harder for me to do that because it's just strings. I can try to parse the string and try to tell if it was a success or an error. But that's, there's other things we can do that are better things that we can do. So we can use generics to try to accomplish something like this. And this is a pretty common pattern that you see emerge in when you're dealing with network responses in Swift. And if you create this enum, a lot of people do this now, they call it result, which has kind of become sort of almost a convention for getting a response back. So I've got an enum called result, and enum, it's got a type parameter, right? It's got a T in there. So this enum is able to work with this type just in the context of things happening with the enum. And that type is T. So I've got a case called success that takes in data of type T and is able to do something with it. And then here, I probably could have gone a little further and made error to take the actual error type and be a little more correct with it, but I wanted to not focus on too many things at once. We're just focusing on that one thing now. And so we'll still just return our error logs as a string for this example. So then what I can do is when I have my closure, my completion handler rather defined in the declaration of that make request function. What I can do is I can say it doesn't take a string into that completion handler anymore. It takes a result enum, and I'm sort of forcing the type at that point, right? When I declare that, I'm saying it's not going to be just a generic thing going in. It's going to be data. It's going to be a type data. And if you haven't played at all with Swift 3 and any of the betas, that's an actual type in Swift 3. That was one of the new things that they had. It's basically just NS data, but it's kind of a Swiftified version of that. Cool, so my completion handler now is going to take in this enum called result. And if it has to replace t with something, it's going to replace it with the type of data. Cool. And it also has that error case where we can just deal with a string. So then what I can do is, inside, before we go into the actual implementation of the request body, we can look at the response handling. All I need to do, because it's going to take that result in from the completion handler when it's called, all I need to do is switch on the result. And I have two cases. I have the case of success and I have the case of error. In the case of success, basically what I'm doing is I'm just pulling out that data, doing something with it inside the response block. In the case of error, I'm just printing out the error with a little bit of a message. So then inside of this make request function, I have already set up these completion handlers, except now instead of passing them strings, I can pass them these enums. I can say, hey, send a completion handler the case error with this message, this string message. And those types match, right? When I'm calling it, I'm calling the error enum with a string argument. And my result enum is expecting a case error with a string argument. So everybody's happy. Compilers just going to be loving that. Same thing when I get inside of the body of this response. Inside the data task, I can just call the error again and pass in that string. Everybody will be happy. I can even send one if I don't have the data returned back. This is pretty cool, right? Like I kind of built this way to track if my response was good or bad and pass the appropriate messages in accordance with that. And then finally, when I call success, that's kind of the easiest one, because I have my data handler inside of that response block when I call the function. All I need to do is just call my completion handler, pass it the success case, and then pass it that data that came back as the argument for that success case. And that's that. My network request is just going to work fine now. And I'm able to control, like if I have more success cases to call based on other conditions inside of that request body and response body, I can. If I have more errors that I want to call, I have a really easy way to do that. I built this logic and control into my application, and I'm using generics to do it. Because I might have another network request where I don't have data coming back, I have some other type coming back, and I've got this enum that can handle it. Now I don't have to write like result data enum, result string enum, result integer enum. I've just got one type that can help me control all of that information. Cool. How much time do I have, Ben? Okay, cool. I am going to show this then. I have a little expert example. I figured it'd be cool if we have time to look at it. We do. So this is another example that I think is pretty cool. And so what I've done with this is, let me bring it up a little bit more so you can see it. Sorry. Is that a little easier to read now? Is that good enough to read? Does it need to go higher? Good? Okay, cool. So I just got this really simple application. I pulled out, all of anything that would be, confusing to just this example. Pulled it out, trying to make the simplest bare bones implementation of this. So what I've done is I've created a generic data source that you can use as the data source for any table view. Doesn't matter what type of data you pass into, it's kind of a starter kit for that. So I'm kind of modeling it after the Code School app a little bit. So at Code School, we have this idea of courses and screencasts, and they're different things, but they share some common, attributes. Like a course has videos, but it also has other things. A screencast just has videos, it doesn't really have anything else. So in our app right now, we're not actually using generics, but we're thinking of ways that we can incorporate this in a little bit better. We've got like a screencast view controller, a screencast data source, a video view controller, a video data source, course view controller or a course data source, and we're kind of duplicating a lot of code because the data source is the same thing all the time, right? It's just self-row index path, number of rows in the section, all those kind of common methods to that data source. So would it be cool if we could just put that all in one place, not have to rewrite all of that code over and over again. So this is the app delegate. All it's doing really is it's just creating one of these two types of table view controllers right now for the same example. It's pushing kind of navigation controller, and it's just showing that. So if I run it right now, it'll show one of those two table view controllers. So I'll pull that one up. So here's what that table view controller looks like. Pretty simple, right? Not giant like most table view controllers when they start out. So I did declare a private class cell at the top. This is something that I probably would do in storyboard or zip, but I just wanted to leave it all in code, so there were like 1,000 places to look. So that's just a UI table view cell subclass right here that just shows stuff with a subtitle style. That's all that code is doing. So I can get two labels. And then in my table view controller, I just start by declaring my data source, and I'm using the special class that I made called generic data source. And then it's taking in, it's got an initializer that takes in two things. It takes in a set of items, which in this case is coming from this struct called mock data. And I put .courses in there. I'll show you what that looks like in just a second. And then it takes a completion handler that the response runs from. And then it's in that response that I'm pulling out the information to show inside of those cells. It just takes in a closure that takes in the course itself and the cell. So like all the implementation details of the non-generic parts of this table view are in this little tiny part that I've just highlighted right here. Everything else is just sort of common stuff that will happen across all table views and any other data source, any other type of data. Sort of defining just my little specific details that are not generic inside that one little block. So I can make the rest of it generic, and I don't have to rewrite it 1,000 times. Then, of course, in my view did loads, since I'm not using storyboard, I have register my custom cell, get a use identifier, and then I just set my table views data source to this new custom one that I just created. So inside of this generic data source, this one's it's like deceptively simple, right? I have pulled out a lot of the other things that I would probably need in a complete implementation, but this is like the bare bones working implementation of this. So I have a class called generic data source, and it's of type NS object, and it conforms to the table view data source protocol. Table view data source, which means I have to have those two methods, right? But it's also got this type parameter here. I'm going to call it item. So what that means is that inside of the body of this class, I can use items as an abstract type, and the compiler won't get mad and say, "What's an item? I don't understand." And furthermore, depending on what data type I'm using, I can pass any arbitrary data type in there and have the table view still load and still work the right way. So inside I've declared an array of items. So anytime we have a table view, there's going to be an array of something that's displayed as rows. So I'm keeping it very generic and just saying yeah, it's those items. And then I've also got a configure cell block that I can pass back. It has an item, cell type, and that's what I was calling in response a second ago. And I'm using that here in my initializer so that I can call it from outside. And then here in my two actual data source methods that are required methods to implement for this protocol, I just return items.count. Again, it doesn't care what kind of item it is, just whatever is in there, items.count, for the number of rows. And then I just return for the self-row index path method. I just dequeue a cell, call my configure cell function with the specific item that it should use and whatever cell it is, and then I just return that cell, display it on the screen. And then just so you can see it, because I've used it in here, just for the sake of keeping it all organized, I created this mock data.swip file. This would, in real code, this would be where whatever data you have coming back from your model, sort of simulated my model inside of here, so I didn't have to make it too complex. And these are sort of the model, different models we would have inside of our screencasts and course stuff. And then I just created these sort of static properties on mock data that I could call to load that data into either of those tables. So just stuff like course title, what the video ID is, how long it is, stuff that we probably use to update the view in our app to show you how many minutes the video was, things like that. And that would be coming from whatever your actual truth of data would be in your app, maybe core data or maybe just SQLite, something like that. Okay. So before I show it running here, because it's not very amazing to watch this running, it's just going to be a table view with some of these this text and stuff inside of it right now. Here in this one, right, I was doing this. I was calling this data source. I was passing it in my course data, and I was configuring the cells, updating the data in the cells based on the data that's returned. So in my screencast table view controller, it's actually kind of the same thing. In fact, if I scroll them in the same way, let's see if it lets me do that now. Here, let me just flip back between them since they're all the same. So see, as I switch between these, these are two different files. They're doing different things. There's not a whole lot changing in there, right? The main thing that's changing is I've now had this, different table view controller name, and I'm passing my screencast videos data in there instead of my course videos. And those are different data types. Like if I go back here, right, course, that's the structure of the course. It's got an array of videos. It's got a path of the title. Screencast video doesn't have an array of videos. It's just one video. It's got its video ID in like 10 seconds. But because I've got that generic data source, I don't have to make a second one. I don't have to say screencast data source, course data source. I don't have to make any of those custom ones. I can just make it all generic across that one type. So if I just go to the app delegate, I'm loading the course table view controller first. I just build and run really quick. Really quick, it's a silly thing these days, and build and run, but there we go. This is the one that was looking at courses. So I just wanted to link 2 of our courses in there as sample data and the path that they belong to. And then if I switch this over to screencast table view controller, build and run again. Now it's pulling in 2 of the screencast videos also with their path from that data source. But one generic data source that I used for both of those. Didn't have to go and rehook anything up in between them. And there's even people that have taken this further. I've seen like videos where people take it further and they make the entire table view controller a generic view controller also. It's like I just kind of stopped at the data source, but you can really take it to the extreme and make everything generic everywhere if you want. It's just that if you make things generic, like generics aren't just a catch-all solution for every problem in the world. It's not like I'm just going to write one class and I'll just make it generic that runs with any data. Right? It's got to kind of make sense to do that. Data sources make sense because at the end of the day, they're really just sort of taking in some model of data and displaying some of the properties of it. So it kind of makes sense to not have to be rewriting that over and over again. But other places it might not make as much sense. Cool, so if you wanted to keep learning about generics, this is like sort of a brief introduction. I did that on purpose because I didn't know how many people would have had experience with this already. When I first started learning, I've been doing iOS development for years, and it's a very new topic to me, right? And I came across it and I was like, wow, this is really crazy, what is this? And I learned how to swap my 2 integers, and it's what now? So I wanted to provide a little more direction and context after that. So the Swift Programming Language official book is of course a great place to start. It goes into all the different ways that you can use generics. There's even a couple of cases that I didn't include here, like including generic types inside of protocols. You do that with something called associated types. And there's a lot of power that you can achieve with that as well. Chris Eiloff and all the people that he works with have an awesome series of advanced Swift books and functional Swift books, and they even have like a video series online now. Talk.objective-c.io. He's one of the people behind objective-c.io. And they've got awesome resources, and they go way further down than you probably even understand at first glance if you're like me. So you're going to watch them over and over again, and read them over and over again, and keep trying to introduce those concepts into your code the best you can. Austin Zhang has a really awesome blog post series that's a little bit older now. So some of the syntax hasn't been updated for Swift 2 and 3, but a lot of the concepts are really strong concepts, and they're still sound. With the Swift migration tools, you'll probably be able to update the syntax errors in the code pretty easily because they didn't make too many changes to them. And then, of course, just find something in one of your apps and start small. Or even in somebody else's app, right? Find an open source project that maybe doesn't include any use of generics that you think you could improve the quality of that code, and the readability of that code, and the maintainability of that code by adding them. And then, put something together, submit a pull request, see what happens, start a conversation about that. So, hope you learned something about generics. Thanks, everybody.